So we're talking about linear algebra. We got to start by talking about what is a linear equation. So we would say that a linear equation of the variables x1, x2, and xn has the form a1, x1 plus a2, x2 plus dot, 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 plus an, xn equals b. What I want to point out is that these guys right here, these guys are our coefficients. The tablet is new to me. Is that coming through okay? Can you guys read that?
Yeah, we can read it.
Okay, very good. So how many variables are there in this particular equation? From Seche, I've got n, also from Felix. And so it's the index on the x tells you how many variables. Okay, so we want to circle the linear equations and state why the non-linear ones aren't linear. So which of these are linear? So I've got, everybody looks like it's in agreement that A is linear. Good. I've got some D's. I got some D's. So here, D is also linear. You'll notice that you have this square root here in the equals, but this is telling you that the B is equal to square root of 2, and that's okay. Why is B, or equation B, not linear? What's the issue with the B equation?
The square root.
Yeah, it's the square root of the variable, right? It's the square root of the x1. And then what's the issue over here in C?
It's multiplying the x1 and x2.
Yeah, it's that, exactly. Sweet. All right, so that's linear equations. Maybe we should just call it good for the day, right? And take our final exam and be done. So then a system of linear equations is what we're going to spend some time on. System of linear equations is a collection of one or more linear equations with the same variables. So here would be an example where you have 3x1 minus x2 minus 4x3 equals 3, and then x1 minus 5x3 equals negative 2. This is a system. Would this particular equation have a unique solution? Have a unique solution? How do you know? Just using some of your beginning algebra skills. So you have 3 variables, x1, x2, and x3, but only 2 equations, so there's just not enough information. So a solution, the answer is going to be no. So a solution of a system is a list of numbers that makes every equation of the system true. If we wanted to verify that 3, 2, 1 is a solution to the system, we would put 3 in for our x1, 2 in for our x2, 1 in for our x3, that, and see what happens. So if we wanted to verify, what would we have? Looks like the first one works, and then the second one, 3 minus 5 equals negative 2, also works. So we were able to verify it by just substituting the values in and showing that it works. That tells us that 3, 2, 1 is a solution. We've already said that it's not going to be a unique solution. So we could talk about the set of all possible solutions. And so we would call this the set of all possible solutions. Call this the solution set. We might ask ourselves, like, what's another solution here from observation? 6, 4, 2. Let's try that. Which is just a multiple of what we started with. Will that work? So we'd have 18 minus 4 minus 8. Is that going to be equal to 3? Doesn't look like that's going to work. So that 6, 4, 2 didn't work. That's too bad. Yeah, from Hui, then the right side would also need to be multiplied. Yeah, that did not work. We could guess and check our way to another solution. I think I think we all can see that. One of the things that's going to happen in this class is we're going to learn methods for finding these other solutions. So rather than spending a whole bunch of time guessing our way to a solution, I'm going to say we're going to work forward. And in this class, we're going to learn how to find all the questions in this solution set. I think 1542 might work, or sorry, 542. No, that's not going to work either. Got one from Andrew. Everybody's thinking. Did you try both equations, Andrew? And Seche? Nice. So we've got two more solutions that have come out. But clearly it's a little bit of a guessing game. So I think the main point is we would like a better way of finding all solutions. Let's keep on going. So two systems are considered to be equivalent if they have the same solution set. And from two-dimensional systems of equations in algebra, we should remember that there's actually three possibilities that we can have. So you can have this possibility where you have exactly one solution. You have the possibility of no solutions, the lines never intersect. And then also the possibility of infinitely many solutions when there's two lines that are the same line. And thanks, Seche, for the correction there. So these three possibilities are going to come up quite a bit in this particular class. A system is called consistent if it has at least one solution, and it's called inconsistent if it has no solutions. Of the three pictures, which represent consistent equations and which represent inconsistent equations? Does that make sense?
The first one, the one when the lines intersect.
So this one. Okay. Any other ones consistent? Yeah, the third one's also consistent.
Yep, I agree.
And it's just this second one that's inconsistent. We will represent a system of equations by its coefficients in a matrix. And so this system that we have here will be rewritten as what's called a coefficient matrix. There's different types of matrices that are here. But in this particular case, we will have a coefficient matrix. And so from here, I'm just going to focus in on the side with the x's to start with. I have to erase that in a second. So my coefficients on the x, so for the first equation, will match with the first row. So I'll have 1, 0, -3, and then 2, 2, 9, and then 0, 1, 5. So that will be my coefficient matrix for this particular equation. Okay. And the size of the matrix tells us how many rows and how many columns the matrix has. Okay. So an M by N matrix, we always has M rows and N columns. And then the last thing I want to do here is also talk about a different kind of matrix. So up here we have the coefficient matrix. It's also what's called an augmented matrix. So the augmented matrix is going to include all of the information that's there, including the stuff that it's equal to. And so we'll have 1, 0, -3, and then 8, 2, 2, 9, 7, and 0, 1, 5, -2. For augmented matrices, you can just leave them in this form, but usually we will also write, we usually also have either a solid line or a dotted line here dividing the what it's equal from the coefficient matrix to kind of like separate out the coefficients on the left and the other stuff on the right. That line is in your head. Like you don't have to write that line. It's just kind of can help you. Questions about this vocabulary and what the various symbols mean? So one thing before we leave here, we always write the rows first and then the columns, and usually we'll do it in the lower right-hand corner of a matrix if we're going to write it. So what are the dimensions of this augmented matrix?
3 by 4.
3 by 4. Good. 3 by 4. And then the coefficient matrix is what dimension?
3 by 3.
3.
3 by 3. Notice since you have the same number of rows and the same number of columns, we would call this a square matrix. Trying to get some more vocab in there for you. So we want to describe an algorithm for solving linear systems, which replaces one system with an equivalent set that's easier to solve. Since they're equivalent, they have the same solution set. So let me kind of remind you about how it works when we solve equations. So like you could take equations and you could multiply them by 2 and it wouldn't change the equations. So things might look different, but you'll have the same solutions. You could take a couple of equations and add them together and it's not going to change what happens. And so the 3 operations we're going to use are replacement, we're going to also use interchanging or swaps. Interchange is a long word. Come on, Dust. Swap is a shorter word. And then the last thing we'll use scaling. Scaling, like multiply it by 2, divide it by 3, something along those lines. And so these are the 3 operations we're going to use to solve a system. And so let's start by trying to do this the old-fashioned way, like the way you learned back in high school or beginning algebra, something like that. So what I would like to do first is I'd like to do a replacement step. And yep, so I'm going to do a replacement. This will be way, way, way more writing than we're going to do down the road. We're just learning, so we're going to write a whole bunch. We're going to do replacement, and specifically the thing that I'm focusing in on is I'm trying to replace this second row here with a new and improved second row that does not include an X1. So here's what I'm going to do. I'm going to take that. I'm going to take my first equation, so E1. This is going to represent the first equation. Let me put that in the chat so everybody's tracking. E1 is equation 1. Okay. E1, and I'm going to multiply it by a -2. And I'm going to add it to E2. And I'm going to turn this thing into my new E2. So it's a replacement. So I'm replacing E2 with this new combination. So the first equation stays the same. I still have x1 minus 3x3 equals 8. I'm going to have a new equation 2. So how much x1 is there going to be in the second equation? let's see. So how do I make this clear? Let's write it all out just for the sake of seeing it once. So minus 2e1 would be minus 2x1 plus 6x3 equals minus 16. And e2 will be 2x1 plus 2x2 plus 9x3 equals 7. And if we add those things together, we get 0x1 plus, help me out, my handwriting's not helping me at the moment, plus 2x2 11. I feel like I did something wrong in my arithmetic. Minus 9.
-9.
-9. Thank you. So this is going to become my new E2 because I'm replacing. It's a replacement. So I have 2. And then E3 stays the same. That's a lot of work to do something you've been doing for a long time, right? This isn't like, it's a lot of extra writing. It's going to get better, but we're just doing it the long way at the moment. So we did a replacement, and what I want to point out is that after the replacement, notice that there's an x1 in only one of the equations. Like, that's why I did it. So I got rid of the other x1s. So the next thing I see, and specifically there's a 1 x1 there. Like, ooh, we really like that one. We're going to call that a pivot. It's going to get its own name later. So we like this so much. Now we're going to try to get a 1 x2 in the second equation. So we have that E1 starts with 1 x1. And so now we want E2 to start with 1 x2. So we could do this a couple different ways, but since we're trying to learn this technique, rather than doing something fancy, let's do an interchange. So I see this, see the 1 x2 that's living out there. So we're going to do an interchange. And specifically, what we're going to interchange is E2 is going to swap with E3. So the first equation stays the same, x1 minus 3x3 equals 8. The second equation is now going to be x2 plus 5x3 equals minus 2. And the third one, 2x2 plus 15x3 equals minus 9. Yeah, from Elijah. Yeah, we're just basically being computers here. That's right. So now we have equation 1 starting with an one x1, equation 2 starting with a 1 x2. Now we want to get rid of this random 2x2. Accomplish this. Now we want to of other x2s. And anytime you want to get rid of other stuff, you're going to use replacement. So you might say, what are we trying to get rid of? We're trying to get rid of the 2x2 that's out front. I want this to be a 0x2. That's what I'm kind of focusing in on. And so there's a couple of ways you can think about this, but basically we're going to multiply the second equation by a -2 and add it to the third equation to give ourselves a 0. -2, equation 2, add it to equation 3, turn that into a new equation 3. Can people see do I need to write the scratch work on the side again? So I'm going to have -2 times 1 is -2 plus 2 is 0. So I'll have 0x2s. And then minus 10x3s plus 15x3s is 5x3s. And this will be equal to, all right, so what have we done? We now have the x1 starts with a 1x1, or sorry, E1 starts with a 1x1. We have the E2 starts with a 1x2. We've also gotten rid of all the other x1s and x2s. So now we just need to mess around with E3. So we want E3 to start with a 1x3. And so since we're focusing in on the 1, in the previous time we wanted a 1, we did a swap. This time we'll do a scaling. We're going to either swap or scale. In this case, we will scale. We went back up. Yeah, I'll just leave it alone. So what should we scale by?
1/5.
1/5, thank you. So we're going to go 1/5, equation 3 to equation 3. And boy, it's a lot of writing. And I'm glad we only have to do this one time in the entire class. We have x2. But there's a lot of things that just get copied from one line to the next, right? And we have x3 equals -1. Whew. Sadly, we're not quite done. We got to do 2 more replacements. Oh my gosh. So we got to do 2 more replacements because we've got to get zeros. So zero x3 in E2 and E3. So what do we have? How do we accomplish that? Well, in the first one, we have a 1x3 down below. We got a -3x3 up above. So we can do E1 plus 3 E3 becomes our new E1. And we can do E2 minus 5 E3 goes to our new E2. I think when we do all of that stuff, we end up with x1 equals 5, x2 equals 3, and x3 equals -1. Yeah, this is totally an algorithm, Elijah. This is a version of the row reduction algorithm. Wait, and we're out of time. Oh my gosh. So what we're going to do when we pick this up tomorrow is we're going to do this exact same example, but we're going to use matrices to do it. And it's going to save us a lot of writing. So this isn't difficult. It's tedious. It's really easy to make mistakes, not because your math has issues, but it's easy to make mistakes because you make copy errors, because you make arithmetic errors, things along those lines. This stuff is really designed to be done by a computer. All right, so here's our augmented matrix, and now we're going to go through and do the same types of steps we did before. And so you'll notice that before we did a replacement, what we were focused on was trying to get rid of this 2 in that spot. And so our step was we did negative 2 row 1, sorry, plus row 2. This is going to become our new row 2. And you'll notice here I'm using R's for row instead of E for equation. Not a huge difference, but a difference nonetheless. The first row stays the same. Second row, 0, 15, -9. And then the third row stays the same, 0, 1, 5, -2. If you compare what we had before, you'll see the 1, 0, -3, 8, and the 0, 2, 15, -9, and 0, 1, 5, -2. They're like showing up from like matching what's over here. Pair each other perfectly. Again, what were we trying to accomplish? We had this yellow 2, and now that yellow 2 has been replaced by a yellow 0, which we like. So next up, we're going to try to focus in on this spot right here, and we're going to try to get a 1 in that position. So to get a 1 in that position, we can swap our rows. So we can do row 2 swapped with row 3. Row 1 stays the same. Row 2 is now 0, 1, 5, -2. Row 3, now 0, 2, 15, -9. And so you'll notice that we now have the 1 in that position. Okay? And we'll talk more about the goal, like the structure and the organization moving forward. But we're not quite there yet. So next up, we want to get a 0 in this position. And so to get a 0 in that position, we'll take -2 row 2s. We'll add a row 3, and we'll make a new row. So row 1 and 2 don't change yet in this step. And then row 3 is going to be -2 of the second row plus the third row. So -2 times 0 plus 0 is 0. -2 times 1 plus 2 is 0. -2 times 5 plus 15 is 5. -2 times -2 is 4. -9 is -5. And so we had a 2 in that spot. Now we've got a 0. The process is working along. And our next target, if you will, is this 5. We're going to try to get a 1 in that spot. To get a 1 in that spot, we'll scale the row. So I'll have 1/5 row 3 to row 3. Zero, 0, 1, -1. So we have that 1 in place. And we can then finish off with 2 steps at once. So we can go for this -3 here. We want to take care of that -3. We want to turn it into a 0. So we'll use the pivot. We'll use the yellow 1 to get rid of the -3. So we have, right, is 3 row 3 plus row 2 plus row 1 goes to row 1. These guys are tied together. For that 5, we'll have -5 row 3 plus row 2 gives me my new row 2. Here's my plan to take care of that pink 5. And all told, 1, 0, 0. Thanks. I'm not seeing the chat. I'll catch up with that in a second. 0. And we will have 5, 3, and 1. So what this is telling us in the end is it's telling us that that 1 and that 5 is telling us that x1 equals 5. This 1 and that 3 is telling us that x2 equals 3. This 1 and this 1 is telling us that x3 equals 1. And I think I did miss a negative. So Ryan's question has to do with what's called back substitution. So I think he's saying, could we just say here you have x3 equals -1? Could I just take that and put it back into the other equations and find the value? That's effectively what we're doing. But I would say that I would encourage you to do it this way because this is the algorithmic way of accomplishing the same thing. So if you want to think about it, or if you think about it, Ryan, what we're doing is we actually are putting in like this bit right here, like the 3R1s is actually saying put in, it's like putting in a -3 or putting in a +3 into that equation and adding it. So it actually is accomplishing what you want. It's just doing it in kind of a strange way. Let's keep going. And I want to just jump through the notes a little bit in this next part. So first of all, again, you have these 3 elementary row ops: replacement, interchanging, and scaling. And we would say that 2 matrices are called row equivalent if there's a sequence of elementary row operations, those are the ones that we were just talking about here, that transform one matrix into another. Practically speaking, again, we're saying that all of these matrices that I had on the right are row equivalent because we use row ops between them. If 2 systems are row equivalent, then they have the same solution set. They're not the same matrix, they're just row equivalent, which is kind of a little bit of a subtle difference. So 2 questions that we're going to talk about a lot in this class are these 2 that are given. So is the system consistent? And consistent means it has at least one solution. And then the second is, if a solution exists, is it the only one? That is the solution unique? And so we're going to talk about both of those questions. And so I want to focus in on these next 2 examples. And I think what I'm going to do is I'm not going to spend a lot of time on row reducing. I'm just going to kind of go straight to the punchline on these ones so we can keep moving. So first of all, we're going to turn this system of equations into an augmented matrix. We have 0, 1, 4, -5, 1, 3, 5, -2, 3, 7, 7, 6. Okay. So this is which kind of matrix again? Augmented matrix. Thank you. Thanks, Reagan. Okay. So then we can row reduce it going through those steps. And we're going to talk, again, we're going to keep talking about the steps, but I'm not going to show those steps at the moment. And if I row reduce this matrix for a few steps, I get down to a point where the matrix looks like 1, 3, 5, -2, 0, 1, 4, -5, and 0, 0, 0, 2. This matrix is in a form called echelon form. It's not reduced row echelon form yet, but it's in echelon form, and we'll talk more about that down the road. And what I want to point out is what Croy is commenting on. He says, ew, this is inconsistent. So focus in on this third line here and tell me what that line means. It means from a whole, yeah, from a whole bunch of you, it's meaning that 0 equals 2. It's like 0x1 plus 0x2 plus 0x3 equals 2. Okay. Or 0 equals 2, which is generally speaking false. So we would say, depending on what the question is, we might say that the system is inconsistent.
Okay, I was going to say that.
Or we might say that there is no solution. Sort of like two different ways of sort of saying the same or similar things. Same thing here in example 6. We could write this as an augmented matrix. I like my lines, so they're pretty fancy looking. And we could again skip a few steps and row reduce. I'm not going to row reduce all the way. I'm just going to put it again in the echelon form. And if I put it in the echelon form, I'm going to have 1, 1, 0, 3, 0. The wrong values. From Harpreet, I've got an error somewhere. Did I get it? Does that look good now?
Dusty,
That's me.
X2 on
Second
second row.
X2 in the second row. Ah, thank you. Right here. Did I get it now? Okay, thank you. Okay. So what I want to point out is a couple things. So I want to point out, first of all, that you have zeros everywhere down below. So zeros. And then I want to point out that for each one of these, you have some sort of a number, and then it's going to have stuff after it. Number and stuff after it, a non-zero number, stuff after it, number after it. None of these pink numbers are 0. And so in this particular case, so again, these are non-zero. These are non-zero. Let me make sure it's clear. What am I saying is non-zero? I'm saying that the guys in the diagonal are non-zero. And since those ones are non-zero, you have the zeros below. This particular system is going to be consistent. It's going to be consistent because you don't have the 0 equals 1 thing. And in this case, you'll have a unique solution. It's kind of a combination of things that's giving us the unique solution. And we'll talk more about it later, but the key thing I want to point out here is that you don't have the 0 equals 1. You actually have non-zero numbers along the diagonal. This thing right here is called the diagonal. There's definitely steps missing in the ... but do you have questions about what we have done or correction?
Could it be possible to get a different result?
You could get a row equivalent result. So you could find a different representation that had the same solution set.
So they would be the same no matter what.
They would have the same solutions. I think it is a 2. I think I have it set so it's 1, 2, 3, 4. I think those are the values, Elijah.